So we want to talk about the algorithms in STL. Algorithms is one of the components in the STL library, and we will give an introduction to the main categories in STL, algorithm categories. Up until now you should have familiarity with the following STL components. You should know what containers are, how they actually work, sequence containers in particular. You should know how iterators work, and you should be able to program a bit in STL. And what we're now going to do is the algorithms which actually operate on the containers. The algorithms do something to containers, and we have an overview of the 7 main algorithm categories. So different categories based on what they actually do with containers. In general, most of the algorithms manipulate data in containers. So think of a vector with values. So the algorithms do something with the values. And what you probably see is a lot in C++, people writing their own algorithms and so on. They should be used a lot more, because many of the algorithms are very useful. You can also create STL compatible containers and classes. You can write your own classes and employing some standards which will allow you to use all these 7 major categories of algorithms in STL. So you do not have to reinvent the wheel. This particular topic is outside the scope of the current course. So when you're actually programming, and that's the whole point about C++, you learn C++ by programming, you need to have a number of header files for STL. The first one is called algorithm. So in the algorithm header you've got all the STL algorithms. You need numeric for some of the numeric algorithms. You need functional for the so-called function objects and function adapters we talked about, and also for the auxiliary functions like min and max and swap. These functions are standard in C++ STL. Now, what knowledge do you have to have in order to be able to get used to using STL algorithms? First, it's obvious, of course, is that you have to know what templates are, template functions, template classes. So you have to have some hands-on experience. So hopefully you should have the experience at this stage, because you've done a number of exercises, you've seen some of the examples from my range, class, points, plus some others. You need to have a reasonably good idea of what a function object is, and both its input arguments and the return types, because function objects can have a non-void return type, so it returns an object or a piece of data, but some function objects just change some arguments, in which case they will have a void return type. And iterators, so you have to know what an iterator is and how it works. The general data structures, complexity analysis, the big O notation. So when you say that insertion into a list at the end is order 1, big O1 means that the time it takes is independent of the size of the list. Sorting criteria and so on. Okay, so here are the main categories, and we'll have an example of each one, of course. So we have the numeric algorithms, quite powerful. It's got about 4 functions basically, but they're all customizable. You've got non-modifying algorithms, which do not modify the data in a container, so it's read only. In fact, there's a bit of a wee mistake here. Just let me draw it here. The sorting algorithms are a special kind of mutating. This is incorrect. And the removing is a special kind of modifying. So you just move everything up 1. This is not correct. Okay, so let's start again. We've got numeric algorithms, things like inner products and accumulating values in a vector, for example. Non-modifying, these are read-only algorithms. So for example, give me the number of elements in a vector whose value is equal to 5, for example. Then you've got the next group called modifying. Modifying algorithms actually change the data in a container in some way. but leave the data in place so that it doesn't get sorted. So this saying that sorting is a specialization of modifying is incorrect. Mutating, these are algorithms which do not change the values in a container but actually changes the relative order in a container. So for example, a special class of algorithms is sorting. And the last category are the sorted range algorithms, and these have to do with the ranges, with the containers which have already been sorted, like maps and sets and so on. But I think this will be outside the scope of the current course, which is in fact a beginner's course, you might say, although it hasn't turned out to be a beginner's course, but otherwise it's too much. So we've got numeric, non-modifying, modifying and mutating. These are the ones we'll be concentrating on, and we give 2 examples of each just to get you started. And it's a good test if whether you have understood all of the template and STL theory we've done up until now. Okay, so the non-modifying algorithms, these change. You've got a let me take an example. Which will be the example in the source code I'm be looking at in a moment. So 1, 2, 3, 4, 5 is a very simple example. So what does a non-modifying algorithm do? It leaves everything as it is, doesn't change the numbers, the values, and it doesn't change the relative order. So you use it with the so-called input read access iterators and forward iterators. So in other words, the iterators go from here to here, in the from beginning to the end, and these non-modifying algorithms can be used for all standard containers. There's a subcategory here for sorted ranges, but we're not discussing it. Now, what are the specific non-modifying algorithms in this category? For each is the for each function. Perform an operation on each element of your container. So it iterates over the elements of a container and does something on each operation. Counting the number of elements satisfying certain criteria. These are customizable as well. So you could say count the number of elements, whose value is equal to 5, no problem. Count the number of elements which are even. Count the number of elements which are odd, or any other criteria you want to employ. Count the number of elements which are divisible by 4. So you've only got 1 here, etc., etc. So search for the occurrence of a subrange. You can look for subranges and equality and mismatches of ranges, so min and max elements as well. So that's quite a lot. And unfortunately, we won't be able to discuss everything. I think you should go to eventually the book by Yositis, and you'll see all the functions, or maybe come to an advanced course. The second category are the modifying algorithms. These actually change the values of elements, and so you can actually change. You can actually copy one range of a container to another container, and while at the same time changing the elements of the range. And the major ones are for each, so you can actually use the for each again to actually modify your values, and the transform function we'll talk about later, algorithm. So we can copy ranges, one range into another range. We can merge ranges. We can replace elements in ranges. So just to keep it a little bit practical at the moment, I can replace all of occurrences of 5 by 20 or something. So he actually iterates and changes things. Replace elements with the result of an operation. So using function objects. And you've got many more advanced replace algorithms. As I've said in the example in a moment, we'll just take simple replaces. A special kind of modifying algorithms are the removing algorithms. Is that in my... Where's my diagram again? The modifying, you see. So you modify something. A real modification is removing. So that's really the value is gone. And the remove elements in a range while copying into another range. So you've got a container. You can copy everything from one container to another. while removing the values from the original container. Don't worry about the associative containers because we didn't talk about associative containers. Okay, and the last remark is maybe not so relevant. So here's the remove elements with a given value or which match a criteria. So you can say remove all the elements which have value 5, or all even elements, or all uneven elements, for example, or anything you want to do. You can remove adjacent duplicates. So you can copy, next one is you copy elements while removing adjacent duplicates, and copy elements that do not match a given criterion. The next category is change the order of elements but not the values. So for example, if I go back to my original example again, just to keep it a little bit concrete for the moment. So I can mutate, so I can sort everything descending, so my values will start at 5 instead of ending in 5 or starting in 1. Okay, so for certain kinds of applications. So here's examples of mutating. Reverse the order of elements, just what I told you just a moment ago. Rotate the order of the elements, so you can actually rotate around. Permutations you can do. You can do random shuffling, and you can change the order of elements based on some criterion which is defined by a function object. The last group is a special kind of mutating algorithm category. These are called sorting algorithms. It changes the order of elements. So they're quite complicated, and in this particular case we need random access iterators. So you've got sorting, bubble sort, and all the heap sort and merge sort, all the sorting routines. So here's an example. Sort all the elements. You want to sort all the elements. Sort and preserve the order of equal elements. So if there are equal elements in the container, you don't sort them. You just leave them as they are. You can do a partial sort. You can sort, let's say, the first n elements of a container, but not the rest. A more advanced topic is convert arrange to a heap. So we can actually create heaps, which is a data structure. We can sort a heap and so on. And finally we got the sorted range algorithms. So you've got a number of data containers which are already sorted to their, according to a certain criterion, so sets and maps, and these are much more efficient, but the we want to not discuss it in this particular case. The numeric algorithms, there's about 4 algorithms which are useful. So the numeric algorithms are meant for containers whose data type, underlying data type, are numeric, and they are very flexible, and more flexible than what they seem at first sight, because the use of function objects and operator overloading is present. So here are the examples and the algorithms in the numeric algorithms. We can combine all the elements, we can sum all the elements and get the products, division, everything, inner products and variance of inner products, partial sums, and adjacent differences. So we can combine elements with their predecessors. Okay, so these are the categories. Let me go back and just review it a bit. So what I'm saying is here, if you're writing algorithms and you're working with vectors and lists and STL containers, or even your own containers eventually, and you want to find some algorithms, maybe STL has it already. So numeric stuff for non-modifying your container, just reading your container, modifying your container, removing elements from your container, changing the order in some way like sorting, and so on. So this is very important that you know it, and try not to reinvent the wheel yourself, because it may have already been done in STL. Okay, so the function objects, you'll see some examples in a moment, and we've talked about it already. The function objects, these are like function pointers, but they are classes, so they have actually got state, but the defining characteristic of function objects is that they actually implement the function call operator overload, bracket open, brackets close. So when you call them, you have f is your function object with some input parameters. It looks like a normal function, but it's really an object. And these are used extensively with STL algorithms. They can be used as sorting criteria, and as I've said, they have internal states. A special kind of function object is the predicate, and a predicate is a function object which returns a boolean, like true or false. In STL there are predefined function objects for multiply, division, addition and so on, which you can actually use in combination with your STL algorithms and containers. Something down the line, which is at the moment of writing the standard C++ 0x standard, we can use lambda functions, and lambda functions are nameless functions which you can use without having to create code to implement the function. So it's just the in situ, on-site functions. But this falls. This is outside the scope of the current discussion. Last remark is the string algorithms. In the C part of the course we talked about strings, and STL has strings, functionality for string. Pretty limited scope for doing the things you might want to do. So if you're working with strings, which is part of STL, it's better to use the boost string algorithm, and it's got lots of functionality for converting strings to uppercase, lowercase, removing white space, trimming white space, finding substrings in a string, substituting a string by another string, splitting and joining strings, and so on. So if you're doing a lot of string manipulation, I would go for the boost string algo, and the boost library we'll be discussing in part 5 of the course. So we take a summary. So we've given a global overview of the algorithm categories. Unfortunately I can't discuss everything. It's probably not good that I discuss everything. So it's for a long-term project for the next 20 years, for example. So 10 years, 5 years, whatever. I think the mathematical algorithms like accumulate, inner product, and partial sum stuff might be useful, and for certain applications you might need to sort your containers. So here's a very simple example. Explain the following. So what's going on here? So that's the question. After the break, I'm going to go into some source code now and come back to the quiz, and you tell me what's going on here. So we'll start my Visual Studio project now. Okay, we're now ready for a demo, a real life demo, and I've got some examples of the different kinds of algorithms and different categories for you. I'm going to go through the code just piece by piece, and the basic idea is, since it's not an STL course, but I feel that you need to learn a bit of STL because it's the icing on the cake, because it tests all your knowledge of templates and C++ programming and so on. So we go through the steps piece by piece. I hope it's not too difficult, because it's quite a lot of stuff to do. We've got about 8 algorithms, and 2 algorithms in every category, more or less, as I hope representative examples of what how the other algorithms look like, and hopefully it will motivate you to go off and buy Yositas's book and try out more examples as time progresses. Okay, so I have a test program. Just let me run it, just let me rebuild just to see if everything's okay, you know. So even I make mistakes, so let's see if it works. I get some warnings and so. We should really look at the warnings. So let's look at the warnings in real time. So I've got an integer unsigned. Basically, we talked about unsigned integers in the C part. Integer can be signed, it can be negative or positive, and the underlying types for a vector is unsigned basically, so it's a bit of a mismatch, so it's a bit sloppy, but I will just leave it. So the application builds, let me just run it just to see if everything's okay. No runtime errors. Wow, no runtime errors. So okay, so it works. So I'm going to go through the steps now, so you believe that something's working. Whether it's logically right or not, I have no idea. We have to look at the code now. Okay, so my first category of algorithms are the so-called numeric algorithms, and I'm taking the same test case as before. So I've got size here. I'm creating a vector, STL vector of size of a certain size, and I initialize the size. So it's 1, 2, 3, 4, 5, and I'm duplicating on the second element the value 5. So the value 5 will be twice in the array, just to make it a bit more exciting. I can actually print the array here. I've made a print function in a moment. So the first algorithm I want to get into is the so-called accumulate. So what do? I accumulate all the values of the incrementally of the vector, and the initial value is 1. So basically what happens is each element of your vector is added to the initial value, and it's incremented from the beginning of your vector to the end of your vector, and I print the value here. So the value should be 1, 2, 3, 4, 5, 1, 5, 3, 4, 5 plus 1. You'll see in a moment. So you accumulate. Now I've got the next interesting part, so pay attention please. I multiply, I can accumulate, and as I iterate over each element of my vector, I multiply. You see, so I go from the beginning of my vector to the end of my vector. This is all IntelliSense what's popping up now, so I hope it's not annoying you. From the beginning of my vector to the end of my vector, the initial value is 1, and I multiply every value. So all the values are multiplied, and multiply is a built-in STL. You see here, it's a built-in STL function object. So that's pretty useful. So I'm not adding all the elements of my vector up, which is the default value. I'm providing a function object. This means the following: you can provide any function object here, even your own defined function objects. So I can make a million accumulates based on, I can have minus, I can have plus, multiplication, doesn't matter. So you see the enormous powerfulness of STL here, you see. So if you're working with numerical arrays, you'll be doing all sorts of operations on the arrays, multiplying, and you can use the accumulate. So the output is an integer, or the type of the underlying vector. In this particular case, it could be an int. Normally it could be a double, whatever. So it's very useful. So just one function and a myriad of function objects you can provide. In a moment we'll provide more function objects with other examples. Okay, now we have the next part here, the inner product. Everybody knows what the inner product is. You multiply the elements of the array with themselves and add everything up with an initial value. Normally the initial value could be 0, so when you're adding something up you start at 0. Depending on what it is, if it's multiply, the initial value will be 1. If it's addition, the initial value will be 0. So it's a bit of mathematics basically. So everybody knows what the inner product is in mathematics. Here's the second one. I'm now defining, this is a complicated one now, because I'm defining a second vector and I'm creating the inner product using outer and inner operations. So the inner operation will be the how the individual elements of vec and vec2 are operated on. In this particular case it's multiplication. You see, so the individual elements are multiplied with each other, and after you've multiplied you actually add everything up, so it's a plus. That's pretty cool. So you could write it in maths. So it's a sum of products. I suppose that's a good way to write it. Just let me write it down here in case I forget. So what we're really doing here is a sum, because the sum is the outside. Sum of, let me see if I can write it properly, products. Okay, pretty cool. You can get a product of sums just by using the plus on the inside and multiplies on the outside. These are just built-in types. So let me write it down. Question mark. How would you write a, the other way around, product just a little exercise for you just to show it, so you can see you can actually play around. This is runnable code that you can adapt and use yourself, right? Okay, these were just 2 examples. There were about 4 more, 2 or 3 more examples, I think, in the numerical group. So this is very powerful when you're working with single vectors and also 2 vectors maybe. The non-modifying algorithms we talked about, of course. These are the algorithms. I've just got 1 example or 2 examples for you. Count the number of elements equal to a given value. So you're just iterating over your vector, and you're counting the number of values which are equal to 5. So I think it's going to be 2 because my vector vec has 2 elements whose value is 5. Again, what we showed a moment ago, you can put there's another option at the end here. We can use a function object, so you can count the number of elements which satisfy a certain Boolean condition, for example. In other words, is it even, is the value even or odd? So you create a function which will tell you if a value is even or odd. Again, you would get a myriad of possibilities with count, you see. And it's a non-modifying algorithm because you're not changing your vector, you're just reading it. An interesting one here is the following. And in this case, you need to know a little bit about iterators, but we've spoken about iterators already. Find the first element in the container equal to a given value. So my search value is 5. He finds it twice. Well, he finds the first one. And so I go from the beginning of my vector to the end of my vector, and I look for the search value. So it gives you an iterator, so it's pointing to the position in your vector. A general remark is the following: if you're searching for something in a container, in this particular case a vector, you get an iterator. So you get the iterator for free. We've seen this already. If the iterator has gone to the end of your vector, the value, it means the value has not been found. It's at the end, it's in the middle of nowhere. So you'll say here value not found, you see. And if it is found, you've got them. You've got the iterator. So when you dereference the iterator, you know what dereferencing is. It's not a pointer to the object, but it's the object itself. Then you dereference and you can print the value. You can change it later on, and if you change, I don't like the number 5, I want something else, you can change it. So this is the non-modifying algorithm. Just let me run it and see if we can get the code here. Let me put some stars here just to accentuate the fact that we're concentrating now on just the modifying algorithm as a test case, right? So which one am I going to get? Presumably 5, because 5 occurs twice. So let's see. Value found, and he prints the value. Let's hope it works. Wow, pretty good. Value is 5, you see? You're proud of me, right? I'm now going to say, what about the value of 999, which doesn't exist? Whatever, 99. Okay, so let's run it again. He'd probably say, I cannot find the value. It's at the end. It's the end of my vector. What? It's not correct. So I'm doing something wrong, I think. Maybe I need to rebuild it. Hold on a sec. It should give a not found value, but anyway. If it works the same next time, I send a bug report to STL. Still a value 5. Oh wait a minute, number of elements equal to 99 is 0. Okay, and it still gets the value of 5. Okay, so that's a bit strange. Oh, wait a minute. Oh, it's the wrong one. Oh, sorry. The value should be here, 99, right? It's twice. Stupid me. Well, to be honest, it's going to happen to you, but it's okay. That's life. When you're tired and it's late in the evening and you're programming, you need to take a break sometimes. So let me just run it again. Wow, pretty good. Value not found. So we're saved, eh? You forgive me. Okay, so these are the non-modifying algorithms. So that's a useful. These are patterns, in fact. In fact, what I'm talking about here can be used in very many applications. So it's not just here's a simple example. You got to think about it and carry on. Okay, now we've got the following. Now it's getting a bit tricky. I've got modifying functions. I got in principle a for each. That's a very useful one. So instead of making a silly loop, you know, for which we showed already, we can just say for each from the beginning of my vector to the end of my vector, I multiply by 2 with an integer, because vectors have ints. What do I mean? I'm going to multiply every element of my vector by 2, but this is my own defined function. So let me go back to the very beginning. It's up here at the top. Multiply by 2 is a function object. It looks like a function pointer because it's got the operator overloading. So it's got the it's a modifier function here. So you have here, where is it? Multiply by 2. It's a void function, you see. So it's something with which it turns a void, and you see here it's a reference, right? So it's a reference. So t gets changed. You see, t is t by 2, multiply by 2. So after the call, it's called by reference, not a const, because a const means you cannot change it. After the call, the for each calls this function for every element in your vector, and that's why it works. So it's multiplied by 2. The next one is a modifying function. So your vector has been changed. It's a completely different vector. Everything's twice as large. That's why it's a modifying algorithm. It changes the data in your vector. The next one is a transform, very useful one. What I'm going to do now is it's going to overwrite itself. So I'm going from the beginning. Here's my input, the beginning of my vector. I'm going to the end of my vector, and from the beginning I'm going to overwrite from the beginning. I'm going to square every element of the vector with itself. So squared. And square again is my own function object. It's probably in might be predefined in STL, but I'm not sure. I don't know. I don't think so. So here's my square function. So what it does is for every input argument it produces an output argument. So it doesn't change the object as such. It creates a new object and puts it into my new vector from the beginning. So I just say t by t. I put a lot of work into this, making all these programs for you guys, so pay attention. Are you paying attention? Okay. This was the transform. The next one is replace. What do you mean replace? It's also modifying. Just to be a bit more exciting, I'm creating a vector of characters. You know what a character is from C. I'm creating a vector array of characters, all of whose elements are equal to d. Okay, it's not very exciting. Later on you can put different numbers in and so on, but anyway, the old character is d, which was its value. The new character is uppercase d, so it's a stupid way to convert everything to uppercase. So what I'm doing is the following. From the beginning of my vector to the end of my vector, I'm replacing the old character by new character. So you've got the replace here. So that's very easy. At least the code is easy to understand. You've got to get, it's like everything else, you need to practice playing around with the code. So the modifier functions, there are some more, as I've said in the book by Mr. Yositis. Things like Okay, we have transform, we have replace. You can swap, you can generate data, you can fill in data, you can remove data, and so on, which I haven't discussed here, but it's, as I've said, it would just be too much for a beginner's course. At least you've got a head start. If you know all these STL algorithms, you're doing pretty well. To be honest with you, I'm not sure if, in fact, I've trained a lot of people all over the place, but a lot of people don't use STL algorithms. So you've got to, if you say you know STL pretty well, and this is a good start, it should be pretty good for your prospects and your own knowledge and so on, whatever. The mutating algorithms now, that's the third group. Mutating elements, as I've said, do not change the values in your container. They just shuffle it around or rotate it or do something with the values. So the values don't get changed. Typical one is I've got a vector 1 to 5, and if I do a reverse, I get 5 to 1. So this reverses everything. I can also, so here's the first function, the reverse. I can rotate elements in the sequence. So here I've got a number of elements 1 to 8. So I can shift like a circular shift. I can shift to the left or the right, right? And so here, so shift is positive. So what I do is rotate from the beginning of my vector. Beginning plus shift, so you can actually add a number to an iterator, and I go to the end, so it rotates it one way. And if it's negative, I do the same as before. So it's really the same code here. So there must be yeah, it's the same code. So I could just presumably I could just call the function irrespective of the fact of it's positive or negative, but you play around with it. So let me say, here's a little exercise. Is this code is the code here, is it redundant? Can I just call one function and get the same results? Try it out. You can run it again and just try it, because the code's working. At least when I gave it to you, it's working, and it's up to you to keep it working. Okay, so let's just run everything again, see what happens. You can look at the output, of course. Let's run it. So you see all the output here. It's check that the output is what you would expect it to be. Yeah, you see here, for example, the vector of characters. Everything's uppercase. Okay. So the vector reversed and whatever number of shifts. Let's give it -4, see if it works. So it's rotated. You see? Yeah. So it's it was 1, 2, 3, 4, 5, 6, 7, 8. Let's run it again just for fun. We're almost finished now. I'm just playing around just to sort of help you. If I do 0, oh, I just got 1, 2, 3, 4, 5, 6, 7, 8. Right. Let's run it again. Let's shift it by 1. Hey, pretty good, isn't it? You like it? Let's shift it by -1 now. -1. So it probably goes the other direction. Wow, pretty good, eh? So you bring the 8, you go in the opposite direction. So whatever. There are a number of issues to attend to. You have to learn how to program all these algorithms, and you have to interpret the output as well to see if it's correct. So that's pretty good. Just last remark about mutating algorithms. You can also have permutations as well. So if you know a bit of group theory and maths, you can actually permute your vector. I can also do random shuffle. I can actually using a random number generator to actually random shuffle all the elements. It's called random_shuffle, but it's something you need to investigate. As I've said, get the book by Mr. Yositis, or I use it quite a lot. Okay, conclusions. The diagram here, we got the numeric algorithms, pretty useful. Non-modifying algorithms, modifying and removing algorithms, mutating, and a few others, but we've concentrated on the most important ones. And the power of STL algorithms is that you have a number of algorithms to do certain things, and you can provide the algorithms with your own function objects, or the function objects as well, in STL itself. So we're kind of finished now, so we'll take a break, and good luck with STL algorithms and containers. As I said, I would concentrate, build your skills up in STL for sure. Object-oriented programming is important, C is important, but certainly all this template stuff and containers is very useful. Okay, so good luck, and you've got some exercises as well, so we'll be seeing you as well. Bye.